Well, let me kick it off, first of all, with the AAS meeting in Pasadena. Now, I didn't attend in person. I attended virtually. I didn't feel safe going there. I had my vacation planned. So I thought, well, let me just attend virtually and I can watch the talks online. I can interact with folks and I can watch the press conferences. And this is what that online login screen looked like when you logged in online. And I want to start with some of the science that actually is near and dear to my heart. Andromeda as a stepping stone to the local volume, chemodynamics of an extragalactic tidal shell. Woo, that's a lot of words there. Well, what's going on here from Ivana Escala is looking at the outer areas of Andromeda and seeing where some of the features in that halo come from. Now, believe it or not, you look down here in the corner, Carrie Gilbert, Mark Fardell, and Raja Gupta-Kurta and Robin Sanderson. Well, those were some of my colleagues back when I was doing research. In fact, Raja Gupta-Kurta has been with us here at All Space Considered before. He was my PhD advisor, and he and I kicked off this research all the way back in, gosh, I guess it was the 90s. It's been a long time now, but we were the first ones to get spectra of red giants, and that was my PhD thesis. So this is an update on what's been happening in this topic since back in that time. It's some amazing stuff. We started looking at these to figure out how do galaxies get bigger. And when we know galaxies collide, these are some pictures of galaxies that are colliding and they merge together to get larger and larger. Sometimes the mergers are big events with equal-sized galaxies. Sometimes they're smaller events with little dwarf galaxies coming in. But we know that big galaxies get bigger by eating the neighbors. And when they do that, they leave behind debris. And you can see here on the left-hand side, Andromeda, the visible image of it is down in the center, very, very small. That's, several full moons across, but there's a lot of enhanced brightness around it that has been seen, the giant southern stream. Now, each of these colored dots is actually the M31 halo fields where they've gone and gotten spectra using the Keck 10-meter telescopes. The spectra were gotten with a big instrument called DEIMOS, and they have over 20,000 red giant stars now. In my thesis, I think we had 29 of them. So they've increased it roughly by a factor of 1,000, which is amazing. And it's over 50 one-hour pointings. And they're able to get the radial velocity of the stars, so sort of how it moves towards and away from us, the positions on the skies, and then the colors of the star tells you about the chemical composition. Now, here's a zoom in of the inner region. You can see the right-hand image, the black and white one, sort of the gray fuzziness surrounding the disk of M31, and yet it's not smooth. It's not a big smooth halo around there. It's definitely clumpy. And there's a northeastern shelf that's been circled in red that sort of ends abruptly. It's some brightness and then it gets dimmer. And the thought was, is that related to sort of the giant stream, the GSS, which the green fields are kind of off on the bottom of it? Did that somehow loop back around? And was it the same merger event that created these? And also the western shelf and the southeastern shelf, there are some pointings of the Deimos spectrograph there too. And the whole question was this one event or was it several events that caused this? So the team went in and looked, and it turns out that they see this wedge pattern when they plot the projected radius of the star. So each of these triangles is now the observation of a single star, a red giant, and the projected radius is how far from Andromeda's center, and Andromeda's the galaxy M31. And on the y-axis, you have the line of sight velocity, so how fast it's moving towards and away from us. And you see it looks a little like a wedge. It's a little bit of almost a triangle feature. The stars furthest from Andromeda's center are kind of tight. They're not very spread out. And as you get closer and closer to the center, the closer to the center is on the left, they have a bigger spread in velocity. Now, if you look at that, and they did a second field. So now that was the northeastern shelf. Now this is the western shelf. You can see, gosh, there's still a bit of a triangle in there, but it doesn't extend as far. And now we do one more. And this is the blue stuff is now the southeastern shelf. It also makes a triangle, but you can see the triangles are all embedded in each other. You have one large wedge-shaped thing. You have another one that doesn't go quite out as far. It only goes out to less than 30. And then the last one only goes out to, well, about 19 kiloparsecs. This is indicative of the object fell in and then sort of lost energy as it fell in, looped around and didn't go quite as far out, sort of like water sloshing in a bathtub and slowing down and not sloshing as high up the edges. The red time it sloshed really far up there. The pink time it sloshed a little less far, and the blue time it sloshed even less. And that's what they think happened. Now, this actually matches some models that are out there that were done by Mark Fardell, that he predicted it would come in and make this shape. And so it matches very, very well. And they do believe that it was one single merger that created all of this mess around M31, that it was a very big merger, and it's consistent with the giant southern stream. So a lot of work has gone into this, and we're starting to piece together that Andromeda had something pretty big fall in, and it tore it apart. The tidal forces of the big galaxy tore apart this smaller object and left this debris all around. So very cool work from the team, and a very interesting press conference. The next thing I want to talk about is a survey of pre-main sequence stars and massive T-Tauri protoplanetary disks with the Gemini Planet Imager. Well, the Gemini Planet Imager is an instrument on the Gemini Telescope that actually they were thinking would be able to see young planets being formed in disks around young stars. This is sort of the view of the young star with the disk being edge on, and near the star, the disk is very narrow, and far from the star, it spreads out, and the small dust is close to the star, and the large dust is mixed in the middle. There's gas in there as well. It gets driven away on the edges. Well, it turns out that it's really, really hard to actually image the planets forming. And that's one of the reasons we haven't seen a lot of images of young planets with this instrument like they thought they would. But what did they find? Well, they thought they'd see rings around these massive stars. They're imaging the disk of material. They're looking at that dust around massive stars, and they thought they would see rings in the dust. Well, instead, they needed, first of all, to put their polarized sunglasses on the telescope, and this is an image of the Gemini Telescope off to the left-hand side with some beautiful sunset clouds. But you take the polarized light and you can remove the light of the star because it's not polarized, and you can take it out of the image, and it leaves behind sort of a distribution. And you can see there's a thin, narrow distribution with some more inside and kind of a gap. That's what they thought they'd see all over the place. Well, they looked at 44 stars, and it turns out they didn't see those sorts of rings around any of them where the star was 3 times more massive than the sun. They saw things like the spiral structure around this one. This one here kind of has a ring, but it's just a single semi-complete ring with a bright dusty area in the middle. This one has sort of blobs around it. This one's just almost a smooth disk. This one has material sort of spiraling inward, and this one's just asymmetric altogether. So very, very strange shapes, and they aren't really sure why that's going on. Maybe there's a binary, maybe there's another object out there that's affecting the shape of the disk. Could it be brown dwarfs that are further away? Maybe the higher temperatures of these massive stars are affecting the ice in these disks, and it's changing the way they behave. Or did they just have an observational bias? They happened to pick ones that were weird somehow. Or are these just too young to form the rings? Are there planets down in there forming that will carve out the rings like they expected to see, but they just didn't give it enough time? We're not sure. They were able to find a brown dwarf or two with this survey, but they didn't come across large numbers of young Jupiter-sized planets forming. So interesting survey. The last one I want to talk to you about, and this is the last of thousands of results at this meeting. We only have time to go over so many. The last one I picked out is dust devils and convective vortices observed by Mars 2020 Perseverance. We sent the Perseverance rover to Mars, and the idea is it's supposed to be going and looking for signs of life. But it also has a weather station on it, and it's able to measure the pressure in the Martian atmosphere. Well, the Martian atmosphere is only about 1% as thick as the atmosphere here on Earth, but it still is there. There is an atmosphere there, and it can lift dust into the air if you get a big enough wind, and we've seen dust devils before on Mars. In fact, right here, you'll see, let it load, you'll see here, these are dust devils that were captured by Curiosity. We'll zoom in here, and you'll see a dust devil moving across the landscape on Mars. That's an actual Martian dust devil caught in several frames of Curiosity. Now, Perseverance has seen these too in some images, and it's seen quite a few of them. The question is how many, and what does it do to the science instruments? Well, let's take a look at a result here. The top graph is showing you change in pressure over time. So this is a period of about a minute long, and you can see the pressure starts out and then it suddenly drops to a low area over a period of about 10 seconds. It gets really a lot lower, 6 pascals lower, and then it rises back up and goes back to where it was before. that's the sign that a vortice went over you, a dust devil or a whirlwind passed near the rover itself. And down below, it's showing how many of these had an effect on what it looks like. So not all of them had dust in them. Some of them had dust and it dimmed the amount of light we got, but others did not. It turns out that only about a quarter of them showed dust in the signature. That bottom graph is showing you how much dust was there. So Perseverance saw more than 800 vortices during its first 178 days on Mars. And by saw, we mean detected with that pressure sensor. And about a quarter of them had dust signatures where it's creating enough of a vortex that it was lifting that dust up into the air. And that it created a darkening of the air, about the same as a smoggy day in Los Angeles, they quoted. And I don't know if this is just because they're from Boise and they're kind of giving a jab to LA. My hat's off to them on that one, and very good for them. So now we're going to turn it over to Alan Alt, our wonderful telescope demonstrator from Griffith Observatory that also watched the press conferences, and he's going to tell you some of the great things he heard at this conference. So Alan, off to you.